All right, so we are very excited this week to have Wei-Lun Tsai speaking, and he will be talking about equidistribution of Fourier coefficients of weak Maass forms.
So many thanks for the introduction, and I'm very grateful to Professor Roland and Professor Wegener for this opportunity to speak here. And also thank you everyone for attending to my talk. It's my great honor to speak here. Okay, and today I will be speaking on equidistribution of Fourier coefficient of weak Maass forms. And everything I'm going to talk about is joint work with Riad Masri. Okay. So the first, let me start by giving a brief overview of the weak Maass form. And for half integral weight, I need to introduce the theta multiplier. Okay, so that's a gamma be 2 by 2 matrix in gamma 0 n. And as usual, we need to end the level divisible by 4. And we can define the theta multiplier by the following product, which involve the Kronecker symbol and the fourth root of unity. Okay, and we also need to introduce the weight k slash operator, and we can define the slash operator of weight k for level n for gamma 0 n is by the following. And you can see for half integral weight, the automorphic factor involves the theta multiplier we just defined. Okay, so now we are ready to define, to give a definition of weak Maass form. So a weak Maass form of weight k and level n is a smooth function from F half plane to a complex number field, satisfy the following three conditions. So the first, F is invariant under the weight k slash operator for any matrix in gamma 0 n. And we need F is the eigenfunction for the weight k hyperbolic Laplacian. And last, we need to incorporate some growth condition at each cusp. So that is, there's a non-constant polynomial in q to the -1, such that the difference of f and this polynomial is equal to big O of e to the minus epsilon y for y approaching infinity. So that is, the f has most linear exponential growth at the cusp infinity. And we also need to incorporate the same growth condition for all other cusps. And moreover, if the f satisfies two additional conditions, the first, if f is vanishing on the weight k hyperbolic Laplacian, and the other is f slash gamma is bounded as y approaching infinity for any scaling matrix not fixing infinity. Then we call the F is a harmonic Maass form for weight k and the level n. We suppose only grows at the cusp infinity. And also we let the HK sharp be a vector space, the infinite dimensional vector space of harmonic Maass form for this type. Okay. So next, I would like to introduce a large family of the weak Maass form we call the Maass-Pancaris series. Okay, so for the positive integer n and z in the up half plane and with the real power of s greater than 1, we can define the Maass-Pancaris series as follows. It's defined by the following sum, and you can see the test function is involved the M-Whittaker function with some multiplication to force its growth purely exponentially in y. So, any questions so far? Okay. Okay. So and we know actually this Pancaris series is eigenfunction for weight k hyperbolic Laplacian with the eigenvalue s times 1 minus s plus a k squared minus 2k over 4. And if we evaluate, we plug in s equal to 1 minus k over 2, we can see this eigenvalue is 0. So that means if we evaluate the Maass-Pancaris series at s equal to 1 minus k over 2, we can get the harmonic Maass form. And there are two special cases when weight 1/2 and s equal to 3/4, and the weight 0 and s equal to 1, we mean the values of the analytic continuation of this Pancaris series. Okay. And also, this Pancaris series enjoy the free expansion at cusp infinity. And it's not surprising that the free expansion involve two Whittaker functions, because we know this Pancaris series is an eigenfunction of weight k hyperbolic Laplacian. And in this talk, I will focus on the free coefficient in the third term, a and kn with a plus sign. And if we evaluate at a is equal to 1 minus k over 2, we can actually see the expansion can be simplified in the following expression. So there are three parts. The first is related to the principal part, and the second is related to the homomorphic part, and the last part is related to the non-homomorphic part. And also, we can actually use this Maass Pancaris to generate the whole space HK sharp. And to see this, we can use the fact that each positive waveform can be uniquely determined by its principal part. So to generate this form, we can just pick a linear combination of some Maass Pancaris series with prescribe the same principal part to generate this form. Okay. So yeah, so after this brief introduction to the weak Maass form, so our main goal is to show the following two equidistribution result for the normalized free coefficient I just mentioned, a and kn with plus sign. So for integral weight case, we prove these free coefficients are equidistributed with respect to the Sato-Tate measure on the interval from -1 to 1. And for half integral weight case, we prove these free coefficients are actually equidistributed with respect to the arc length measure on the same interval for p approaching to infinity. And I will precisely state the main result later. So let me first give a formal definition of the equidistribution. So let X be a locally compact Hausdorff space, and mu be a Borel probability measure on this space. A sequence of the finite subset in this space is said to become equidistributed on this space with respect to the major mu if for any given any continuous function, we have that the average sum is approached to the integral with respect to this measure. So in other words, we have the average derived measure, we start converged to the major mu. Okay, so that is the formal definition for the equidistribution. And so the next, I need to give a nice normalization to give to produce the normalizing factor to force our free coefficients actually lie in the interval from -1 to 1. Yes, so we need to produce the normalizing factor to divide to force our free coefficient is lie in the interval from -1 to 1 after dividing by those normalizing factors. And we actually show under some condition that depend on the n and p, we can produce two normalizing factor. The one is for the integral weight, and the other is for half integral weight to give the following normalized free coefficient. Okay, so for the integral weight, we denote by the lambda mksp, and for the half integral weight, we denote by the lambda sub mks for p. So to formulate our main result, we need to introduce some index to enumerate the normalized free coefficient. So given any interval in the multiplicative group of finite fields.
Can I interrupt?
Yeah, yes. Yeah, no.
Where do you get these normalization factors? I mean, we don't have the linear bound or Ramanujan case, or do we have it?
No. Yeah, actually, we can produce this normalized factor by directly bound the Fourier coefficient. So to show the normalizing
that you.
Like, do you divide by the leading asymptotic or something?
Yes, that's right. So we need to divide by the sum, the growth from the main term, to make sure this Fourier coefficient lie in the just less, the absolute value is less than 1. Thank you. Yeah, thank you. So now we need to assign an index set to enumerate our normalized Fourier coefficient. So given any interval in the multiplicative group of a finite field FP, and we choose a complete set of residue classes IP, so such that for each representative MPI, we need to satisfy the MPI is greater or equal to this constant P to the alpha for each I. And so the following, this choice determine our index set we consider. We denote by the S alpha IP. Okay. So now I want to show you about the result for integral weight case. Okay. So let's recall the Sato-Tate measure. Okay. So there's a probability measure defined on the interval from -1 to 1. It's called the Sato-Tate measure. It's defined by the following, and the following picture is related to the probability density function 2 pi square root 1 minus t squared. And now we are ready to state our main result for integral weight case. So give any the interval IP, and with the condition the length should be strictly less than root of p, then given any test function of boundary variation, we have the following asymptotic formula with effective error term. So in other words, we give an effective estimate between the Sato-Tate measure and the average derived measure related to normalized Fourier coefficient. And you can see the error term is bounded above by some effectively computable constant times the total variation, the var f, and times the factor depending on the ratio, the length of IP over square root of p. And you can see if we let the ratio, this ratio approach to infinity, the whole error term will approach to 0. Okay. So that is gives us the following corollary. If we define a sequence of finite subset consisting of the normalized Fourier coefficient, and you can see the Fourier coefficient, the lambda with the index satisfying our setting, then we have the following corollary. It's directly from our main result. So given any IP with the same condition and assume this ratio approach to infinity, then we show these sets become equidistributed on this interval with respect to the Sato-Tate measure.
Okay. And sorry, I think I missed maybe some notation from earlier on. Okay. Is P here corresponding to the level of the form?
Like yes, right. Yes.
And so necessarily prime or not?
Oh, it's prime. Yes, it's prime. Yeah.
Okay.
So yeah, so we consider the prime level P. Yes. All right. Okay. So the next, for n equal to 1 and weight 0 and s equal to 1, and we pick the constant alpha equal to 5.3, and we pick a whole interval IP equal to the FP cross, and we can actually give the following the four histograms to demonstrate the equidistribution for the set consisting of the normalized Fourier coefficient. And you can see in each histogram, the height of each bar is closely related to the total number of the normalized Fourier coefficient in each subinterval. Okay. So now to prove, to give a schedule proof of our main result, the key strategy is to use the distribution of the Cruz-Common sum to study the distribution of the our normalized Fourier coefficient. Okay, so let me define the classical custom sum, and we can see it's defined as follows. It's like the exponential sum, and the d bar is the multiplicative inverse of d mod p. Okay, so use the Wei bound, we know that the custom sum is bounded above by 2 times square root of p. So we can divide by 2 times square of p to rewrite the sum and to be the cosine of some real number in 0 pi. And so we can define the following normalized custom sum. Okay, so we can ensure this normalized custom sum lie in the interval from -1 to 1. And we prove the following proposition is related to the approximation between the normalized custom sum and the normalized Fourier coefficient. So you can see we give the formula plus some error term, and you can see use this formula. We can if we want to study the normalized Fourier the distribution of the normalized Fourier coefficient, we can just study the normalized the distribution of the normalized Fourier custom sum instead. Okay. So if we want to estimate the difference of the 2 measures, we need to introduce the discrepancy. Okay. So let me give a definition. So the average derived measure is defined to be the following average sum, and the chi is the characteristic function of the left open interval. Okay. So now we are ready to define the discrepancy for any set x. Okay, so for any set x with respect to these 2 measures, the Sato-Tate measure and the average derived measure, by the following: we consider the truth of the difference of these 2 distribution functions and run through all the y between -1 and 1. Okay. So if we want to show the equidistribution result, it's more or less to show this discrepancy approaching to 0. Okay, as there's a sequence of x approaching to as the index approaches to infinity. Right. So next, we need to further estimate to for this discrepancy is due to the work of a new writer. He gave the following Equidistribution type inequality for the Sato-Tate measure. So you can see the discrepancy is bounded above by the sum constant term plus the sum double sum in the second term, and the inner sum we call the Weyl sum is closely related to the studying the equidistribution problem. If we want to give the equidistribution result, we need to bound the Weyl sum, and the U sub r is the Chebyshev polynomial of the second column. Any questions so far? All right, so the key to give equidistribution result, the key is to bound the Weyl sum. Sorry, so we actually give the bound for the Weyl sum, and actually we give the bound for the discrepancy. So we need to the following key proposition to deduce our the main theorem. Okay, so we give the bound effective bound for the discrepancy of the set consisting of the normalized Fourier coefficient. Okay, so given any the interval IP with the same condition, the length should be really less than square root p. So we have the following effective bound for the discrepancy with respect to the normalized Fourier coefficient. And so you can see when the ratio, the length of IP over square root p approaches to infinity, the discrepancy will approach 0. So we more or less get to the equidistribution result. Right. So now the key is to know how to prove this key proposition. Okay. So I want to sketch the proof. So we first apply the Equidistribution type inequality for our finite set with respect to the normalized Fourier coefficient, and we separate the bound into 2 pieces. So the first one is S1 is related to the vowel sound. Okay. And the S2, the second part is related to the difference of the normalized free coefficient and the normalized custom sound. Okay. So we first bound S2, so we can use the approximation by the custom sum and the upper bound for the supernorm of the derivative of the Chebyshev polynomial and the mean value theorem, we can bound S2 effectively by this bound. Okay. And to estimate S2, so actually is key, just like I said before, the key step is to estimate this vowel sound. Right. So we need to use the recent work of Fourier, Kowalski, Michel, Raju, Rivet, and Salan Rarajan to give the estimate for this vowel sound. So they prove the bound of the compressed value function, the bound for the sum of a compressed value function on show interval in CK group. So actually, they prove the following bound for the partial sum with some condition restriction for the length of the interval. And you can see the constant C of phi is defined by the maximum of the supernorm of phi and the supernorm of the finite Fourier transform of phi. So once we apply this bound, we can bound the vowel sum by the constant C of phi times the factor depending on the ratio. Okay, and so now the phi of n is related to the Chebyshev polynomial of second kind of the normalized custom sum, and we know this function is actually p-periodic function. Okay, so and you can see on the right hand side in equation 2. So if we want to let the right hand side approach to 0 as p approach to infinity, we need to bound the constant C of phi because the C of phi depends on p. Okay. So actually, we give the uniform bound for the constant C of phi. So this constant C of phi is bounded above by 5 times 3r plus 7 squared, and r is from the R's Chebyshev polynomial of second kind. And the key strategy is to use the different geometric perspective of phi to view the phi is actually the Frobenius trace function for some Fourier sheaf. And if we want to bound the constant C of phi, is to bound the analytic conductor related to this Fourier sheaf. So this analytic conductor control the complexity of this trace function. So we actually bound the analytic conductor by you can see the first bound is actually related to the bound for the analytic conductor. Okay. So it's 10 times some term square. So that is term, the intermediate term is related to the bound of the analytic conductor. Okay. So once we combine this bound, we can actually show the constant C of phi is independent of p. So now you can see the right hand side will approach to 0 as p approaches to infinity, as the ratio approaches to infinity. Okay. And so actually the estimate for the equation 4 is actually can be viewed as a verification of Weyl criterion, because we know this sequence of the Chebyshev polynomial is actually a normal system for this L2 space of the interval from -1 to 1 and the Sato-Tate measure. Okay. So now, plug in the bound for the Weyl sum, we can actually give the effective bound for the S1 for the first part, and combining the bound for S1, S2, we can complete the proof of this proposition. Okay, so to finish the proof of our main result, we just need to apply the following, the Holaka-Coxma type inequality for the Sato-Tate measure. So you can see this inequality give the estimate. The upper bound is depend on the total variation and the discrepancy. So once we give a bound for discrepancy, we can give the bound for this difference. Okay. So now I want to show you our main result for the half integral weight case. Okay. So before I get started, so any question for the integral weight case?
Yeah, I have a couple of questions.
Okay.
Can you prove Sato-Tate for ordinary cusp forms using, well, these all require the exponential growth. So do these methods work at all in the cusp form case, or?
Let's see. So actually, have not explored for that direction, but
well, a lot of times you can estimate the coefficients more accurately for the harmonic Maass form the ones that actually have a pole somewhere, because they grow sub-exponentially and there's a few main terms that dominate everything. And yeah.
okay.
But I guess my other question is, does this, like, I'm interested in these normalizing factors, and that when you divide, you get the Sato-Tate. That's a pretty remarkable phenomenon. So like, does it have any meaning in terms of like L functions or something? Like when you look at the delinear bound and you look at the L function, you have to divide by like the coefficients by n to the k-1/2 to normalize them, which is a pretty natural thing to do for an L function anyway. It's like shifting the power of S. It's not really doing much. And when you do that, you get this nice Euler product with these Sato-Tate parameters. And in fact, like Sato-Tate is a consequence of like symmetric powers of these things having certain properties of their zeros, etc. So like, I wonder if it's possible that like these normalizing factors give something really nice. Like it's there have been people like Katrin Bringman and others, Pavel Gurjoy, who have studied L functions for weakly holomorphic modular forms, but there's not like a comprehensive theory of them. So I wonder if this would be like helpful for trying to define those types of things. And you're normalizing by like dividing by something that's sub-exponentially growing. So if you want nice things like Euler products, you need to have Hecke eigenforms, and these things can't be Hecke eigenforms because what Hecke operators do to the principal parts. But on the other hand, you can have things that are Hecke eigenforms up to the addition of some extra junk weakly holomorphic thing. And since you're dividing everything by these really large, really fast growing coefficients, maybe you can, that kind of doesn't end up mattering, for these distributions. Anyway, I just wonder if you've thought at all about like, this is strong evidence that these normalizing factors are natural or nice in some way. And I wonder if they lead to some natural L function theory for harmonic Maass forms, which is still not a fully developed subject.
I see. Okay. Yeah, that's very interesting. So yeah, I will think more about it. Yeah. Okay.
Okay.
So yeah, so let me start show you about the result for the half integral weight case. So let me recall. Let me introduce the Arc-length measure. So actually, we call the push-warm half measure on the unitary group of degree 1 is given by the following. And you can see the probability density function. This picture is related to the probability density function. Okay, and actually we call it Arc-length measure because this push-forward half measure is related to the Arc-length measure defined on the half circle. Okay. So just to make a change of variable. Okay, so now we are ready to state our main equidistribution result for half integral weight case. So given any interval IP with the length strictly greater than square of p, and we need to incorporate some local condition for the index little n. And if given any test function of the boundary variation, we have a similar syntactic formula as follows, and with the effective error term. And so in other words, we give the effective estimate between the Arc-length measure and the average derived measure relate to normalized coefficient for half-interval weight case. Okay. And you can see the error term is a slightly, we get a log square term, and also the exponent for the ratio is a -1, is now minus 1/3. Okay, but we still can see if the ratio approaches infinity, the error term still approaches to 0. Okay, so now if so that gives the following corollary. If we define a sequence of finite set consisting of the normalized free coefficient satisfying our setup, then we can show the following the corollary if given any interval with the same condition and assume the ratio approaches infinity, then this set become equidistributed on this interval with respect to the Arc-length measure. Okay. Okay. So like I said before, for some weight, like a weight 1/2 and weight 3/2, so it's not easy to produce the normalizing factor. So to produce a normalizing factor, we need to bound to the free coefficient. So we crucially require the power saving bound for some of the half-interval weight Kutztown sum. And this bound is uniform in all the parameters. Okay. So let me define the Kutztown sum with a theta multiplier. So we can define the half-interval weight Kutztown sum by the following exponential sum twisted by the theta multiplier. Okay, and we show the following bound for the sum of the Kutztown sum for weight 1/2 and the weight 3/2, and you can see the implied constant is only depend on the epsilon. Okay. And if the exponent for x is greater or equal to 1/2, we actually cannot produce any bound for the free coefficient. Okay, and the proof for this sum for this bound is crucially used in the spectral method of the automotive form, and especially the Kuznetsov Proskauer formula. Okay, so we need to use the Kuznetsov formula to bound the discrete spectrum and the continuous spectrum, and the main contribution is from the discrete spectrum, and do some estimate, and we can get this power saving bound. Okay, so once we have the normalizing factor, we can to make sure that our normalized free coefficient is light on the interval from -1 to 1. Then now we want to study the distribution of the normalized free coefficient. So similar to the integral weight case, we use the Kutztown sum to study the distribution of the coefficient. So now for the half-interval weight, we need to use the Sato-Tate sum. Okay, so we can define the Sato-Tate sum of the prime p by the following exponential sum twist the quadratic character. Okay, and so the identity due to the Sarnak, we can actually rewrite the Sato-Tate sum by the following, and so actually this identity gives the normalizing factor for the Sato-Tate sum. So we can make sure the Sato-Tate sum is lying in this interval after the normalization. Okay. And so like the integral weight case, for the half-interval weight case, we can prove the approximation formula between the normalized free coefficient and the normalized Sato-Tate sum. Okay, so if we want to study the distribution of the normalized free coefficient for half-interval weight case, we just need to study the distribution for the Sato-Tate sum instead. Okay. So now we transfer to study the distribution of the Sato-Tate sum. Okay. And actually, there's no result for the equidistribution of the Sato-Tate sum. So it's due to the work of Duke, Friedlander, and Harmonic. They show the Sato-Tate sum become horizontally equidistributed with respect to the Arc-length measure. And the word horizontal refers to the Katz Sato-Tate equidistribution or Sato-Tate conjecture for horizontal Sato-Tate conjecture for the Kutztown sum. Okay. So yeah, for the vertical version, we prove the vertical version for the equidistribution result for the Sato-Tate sum. So given any interval with a length strictly less than p, square root of p, and also satisfy the local condition for n. So given any test function of boundary variation, we have the following symptomatic formula related to the normalized systems, the normalized Fourier sum and the arc length measure. Okay. And also we give the effective bound for the error term. Okay, and you still can see if the ratio the length of IP over square P approach to infinity, the error term still approach to 0. Okay. So as the direct corollary, we actually can prove if we formulate, we consider the sequence of finite subset consisting of the normalized Fourier sum, then we can give the similar result for the equidistribution for the Fourier sum. So you can see this set consisting of the normalized Fourier sum become equidistributed on this interval with respect to arc length measure. Okay, and actually this corollary can be is analogous to the CAT's equidistribution result for the custom sum. Okay, and we give some numerical example related to this normalized Fourier sum. We can see there are 4 histograms. Is demonstrate this set become equidistributed with respect to the length measure. And the reason I need to pick the IP to be the contain all the quadratic residue because there's some local condition I need to incorporate in the index M. So I need to consider IP is actually equal to include all the quadratic residue. So that is AP cross square.
I have a quick question.
Okay.
Sorry, maybe it's going to be answered on the next slide. Sorry, go ahead.
Okay, so to prove this equidistribution for the Fourier sum, we need to further estimate for the discrepancy. So that's we can actually use the following Harmonic type inequality for the arc length measure. Okay, so given any set in the interval from -1 to 1, so we have the following estimate for the discrepancy. Okay, and you can see, so now the second term is involved the Wei-Lun sum, but you can see the test function now is related to the Chebyshev polynomial of the first kind. Okay, because now the measure is changed to be arc length measure. So the test function we need to change to be the Chebyshev polynomial of the first kind. Okay. So once we have this Taron type inequality, we can actually give a vertical equidistribution of a Fourier sum from the following proposition. So we can bound the discrepancy with respect to the set is consisting of the normalized Fourier sum is bounded about by this constant times some factor depending on the ratio of IP over square P. Okay. So finally, so let me summarize our main result. We actually prove the normalized free coefficient of a genetic family of weak mass form of integral weight and level P become effectively equidistributed with respect to the Sato-Tate measure in short intervals. And also we prove the similar result for the half integral weight case. Okay. So yeah, that's all I want to share today. And I hope you find it interesting. Thank you so much.
Great. Let's thank Wei-Lun for his talk. Does anyone have any questions? I guess I have a quick one, which was what I was going to ask, but you answered it. So this discrepancy vanishes more quickly for the half integral weight case from what like you have the -1 instead of the -1/3. Do you have like an explanation or an intuitive reason why that should be true or why that is true?
So okay, yeah, that's an interesting question. So let's So if I remember correctly, that's depend on the estimate from the let's see. So okay, so that's depend on the version when we bound the biosum. For the integral way case, we need to bound the biosum related to the Chebyshev polynomial of second kind. I think it's much harder than the bounding the Chebyshev polynomial of first kind. And so
I guess is it truly like, do you expect them to the discrepancies to vanish at similar rates? Like, is it an issue with how difficult it is to bound this thing, or do we, like, from the histograms you put up, it does truly look like the half integral way case, the discrepancy vanishes faster, but that could just be because the pictures maybe look nicer for whatever reason.
Yeah, so actually, yeah, so from the so we can actually get a nice picture, just use a small, use smaller pi p to get for the half integral way case. The reason is just let's see, so sorry. Yeah, so the reason is just how to bound the biosum, and for bounding the biosum related to the Chebyshev polynomial of second kind is difficult. Is much difficult relate to the Chebyshev polynomial of first kind. Okay. So and so for moreover, so like the Chebyshev of second kind, we need to bound the constant of C of B. It is much harder because we need to use some geometric method to bound the constant C of B. But for the half integral way case, the C of B actually can be evaluated by the biosum. So actually can be evaluated by something bound by 1 or by some constant. It's not difficult to compare to the integral way case. We can actually use bounded by, we can evaluate the biosum and in terms of the Gauss sum, and then we can evaluate Gauss sum to get a bound for the constant C of B.
Mm-hmm. Okay, thanks. Any other questions?
I mean, as you know, the Chebyshev of second kind is a derivative of the first kind.
Mm-hmm.
So this maybe explains a little bit that the second kind is more complicated because the derivative. So my question is backwards. Has this any meaning in your theory? I mean that in the integer weight case you have Chebyshev 2 and involved, and in the other one, and also I mean yeah. So is there any interpretation of that or meaning?
Oh, okay. Yeah. Thank you for question. So yeah, so the reason is because we consider the measure for the integral way case is a Sato-Tate measure. So sorry, let's go back to and you can see actually the Chebyshev the polynomial of second kind is also normal basis related to this L2 space of the Sato-Tate measure. And so that is we consider the test function is related to the Chebyshev polynomial of second kind. And for the half integral way, we consider the arc length measure, so which means the corresponding orthonormal basis or orthonormal system is related to the Chebyshev polynomial of the first kind.
Yeah, but for example, in one case you have the density function is going up on the borders, and in the other case it's going down. So that means the size of the coefficients in one case is not the opposite, but you have this one and you have the bathroom tube.
Right.
So is there? I mean, I understand you just use the canonical test function, but
right.
But it's a little bit. It's at least it sounds quite interesting that half integral and integral, they have just these two types of test functions.
Okay.
I mean, 'cause, I mean, I understand you just use the canonical test function, but it's a little bit. It at least it sounds quite interesting that half integral and integral, they have just these two types of test functions. Okay.
Okay.
I mean, 'cause, I mean, 'cause, I mean, I don't know how in the when we have some kind, I don't know when we would have some in the holomorphic case. Of course, we have the Sato-Tate. I have no idea what we have in the half integral rate when we go for the analogy.
Okay, so
Just
I don't think we have something like that. Yeah.
no,
I mean, because there's not like a.
there's no the linear bound, and
Yeah.
and
Yeah.
we know the
Well,
linear proof.
the Ramanujan type conjectures are not known in the half integer weight cusp form case, right?
right.
Well, and we know things like
Yeah.
Riemann hypothesis is not true, but like Lindelof is still believed, and we still don't know a lot of things there. Yeah.
Right.
So this is quite, I mean, quite interesting because this pulsing gives you this normalizing factor, and which we don't have in the holomorphic case.
Yeah.
So
Yeah,
it's
that's
really
right.
quite, as you said, Larry, it can stimulate backwards now the theory of like what Pavel and Catherine are doing.
Yeah. Yeah, I mean, there's a lot of mysteries with like what L functions and things should mean in these cases. So any kind of hints about, what the structure should be could be useful.
But I mean, when you, for example, which I may talk next week about, when you go for just for eta powers, it's to some real power. It seems quite surprising that one needs for the discriminant function or for the Ramanujan tau function this kind of deep theories to prove this bound when you do numerical investigation in eta powers. There's no reason why to the power of 24 is different than to the power of 23.9 or something like that.
Mm-hmm.
Right.
Yeah.
Which is of course, and so you or half integrate when you go to the power of yeah, what like 20, then you get weight. No, not 20. When you take like 15, you get 7/2, and so from that viewpoint, there's no reason why even an odd weight are really different. But when, of course, when you use Hackett theory, of course, it's a big difference.
Yeah.
Yeah, right.
Very interesting.
Yeah. I have another question. Did you do any experiments with these distributions in non-prime levels? Like, do they still look like similar types of distributions hold, or?
No, I didn't do that experiment because the thing is we only know we only know the equidistribution result for the Cruz-Lens sum module P.
Right.
And yeah, so I didn't compute some numeric respect to the any general level n.
Yeah. Well, of course, it would be much easier to prove in the prime level case. It's much simpler, but
Right.
I'm just wondering, like, just by playing around on a computer, can one identify some natural normalizing factor and just see if it like looks like it's the same type of thing or not?
Okay. Yeah, I didn't. Yeah.
But yeah, and I'm also curious about like applications, I guess. So you probably haven't thought about it, but for example, some nice examples of harmonic Maass forms are, for example, Duke Imamoglu and Toth's weight 1/2 harmonic Maass form that you get from cycle integrals of the J function.
Okay.
But in general, you can take cycle integrals of a weight 0 thing, and it's kind of a theta lift that gets you to weight 1/2.
Right.
But I just, that's something geometric. So it would be really interesting if there were some kind of, you're saying there's some there as an application, there should be some like there might be some like equidistribution of these kind of cycle integrals of things of things like the J function, and as a geometric statement, that's already quite interesting and be interesting. There's a lot of things about like distribution of geodesics on modular curves and things like that, and you know, it
Right.
just would be interesting if there were something. What would that statement mean geometrically if it would be interpreted? Because you should be able to apply it to cases like that, hopefully, or even if you can't prove it in those cases, like the non-prime level, maybe there's like experiments one could do that would suggest that that sort of thing is true, and maybe in some case, some examples that would have some other meaning that would be interesting.
I see.
Yeah, but really great stuff. I mean, it's. I think you can tell we're pretty interested in this stuff, and you should pursue it further. Like, you know, what other things are this related to? What is it? You know, what is it analogous to classically? What are the applications? I mean, it's a really nice theory, and perhaps you can you can explore further directions with it too.
Yeah. Thank you very much for comment. Yeah.
Any other questions or comments? Great. If not, let's thank Wei-Lun again.
Thank you very much for coming.